Emission spectra and Bohr model of the atom.
Emission spectra of a particular element is always the same. It consists of the same bright lines at the same characteristic wavelengths and can be used to identify the element. The Rutherford Bohr model is of the hydrogen atom or hydrogen-like ion, where the negatively charged electron confined to an atomic shell encircles a small positively charged atomic nucleus, and where an electron jump between orbits is accompanied by an emitted or absorbed amount of electromagnetic energy.
The emission spectra is a series of different colors of light projected in lines. The light emitted is unique to the atoms of a specific element. This happens when the atoms of an element absorb energy due to a surge of electric discharge or light. It can be used to identify and discover different elements. They can be characterized by the behavior of their electrons, which is shown through the color lines emitted. The first spectroscope was invented by Robert Bunsen and Gustav Kirchhoff, and it was presented in 1859. They studied the sun and chemicals with an emphasis on elements heated by the flame of a Bunsen burner. The dark line, or absorption spectra, was created by Joseph von Fraunhofer in 1814. The spectroscopes we use today are a much more compact and convenient version of the same spectroscope created by Kirchhoff and Bunsen. Spectroscopes separate the light emitted using a prism. A sample of gaseous atoms at a very low pressure are surged with an input of energy, and then emit electromagnetic radiation. The spectral lines emitted can be seen with the different regions of the electromagnetic radiation spectrum. This includes infrared, visible, ultraviolet, X-ray, etc. The Bohr model is a planetary diagram of the hydrogen atom to explain the filling of electron energy levels in an atom. It is designed as the nucleus as the sun and the electrons orbiting it. It also explains how an electron can only give certain energies and how the electrons within the planetary model have fixed distance and energy. Bohr also touched on the quantum theory to explain why these properties exist. Niels Bohr went to work with a group under the direction of J.J. Thomson at the University of Cambridge. They were trying to understand and better explain how electrons work in atoms and the atomic spectra. After Bohr voiced his ideas that more radical change needed to be made to the model of the atom of the time, he was kicked out of the group and went to work with Rutherford at the University of Manchester. Bohr used the idea that the light emitted from the atomic spectra was related to how electrons move around. His first hypothesis suggested a stationary state, meaning that electrons did not radiate energy as they orbited, and that each orbit related to the constant energy of each electron. His second hypothesis suggested a transition, meaning an electron can change their energy by jumping from one stationary state to the other. The transition required the absorption or release of a photon.
Niels Bohr suggested that electrons in an atom were restricted to specific orbits around the atom's nucleus. Bohr argued that the electron in a given orbit has a consistent energy, thus he named the orbit's energy levels. When an electron falls from a higher energy orbit to a lower energy orbit, it releases energy in the form of light. White is not a color of light itself, but rather results when light of every other color is mixed together. Because an electron is only allowed to exist in certain energy levels according to Bohr's model, there are only a few energy levels of light which can be released when electrons fall from one level to another. As a result, the Bohr model explains why atomic spectra are discontinuous. The Bohr model successfully predicts the four colored lines in hydrogen's atomic spectrum, and the Bohr model is no longer accepted as a valid model of the atom, as it is combined with another model. When an electron drops from one energy level to another quantum of radiant energy is emitted, and this gives a line on the hydrogen spectrum. The bigger the energy difference, the greater the energy of light that was emitted, and therefore it's higher the frequency. The energy level for N1 is called the ground state. The energy levels from N equals 2 and above are called excited states. And the level with N equal to infinity is known as isolation state. All the energies are negative compared to the isolation state, which has zero energy. This means that an electron in any of the other levels has to gain a certain amount of energy to reach isolation level, so escape from the atom.
In the early 1900s, scientists made an observation that when a sample of low-pressure gas atoms of an element, specifically hydrogen, has an input of energy such as an electrical current, it would emit electromagnetic radiation or a form of light. This experiment was done through the passing on light through a thin prism. When this experiment was done, scientists observed that the colors that passed through the prism were colors seen in the rainbow. They made this observation using a spectroscope. Only specific atoms with more energy emit certain frequencies. The color was the determining point of the level of frequency that has been emitted. The atomic emission spectrum was formed when these colors and lines were placed as discrete lines. Scientist Niels Bohr used hydrogen gas in a tube at low pressure and allowed an electrical current to pass through the tube. Doing so, the tube gave off blue light. The color bands shown in the diagram below have specific wavelengths that match the colors. The problem with this experiment and the observation wasn't necessarily the experiment itself, it was explaining and describing the process of this experiment and how it was proof to be the creation of the emission spectrum. This is when the scientist Niels Bohr stepped in with the solution. In 1913, Niels Bohr developed the Bohr theory, as they would say. It was important to explain how the electrons are positioned and what makes the atom considered stable. He chose hydrogen, as done in the experiment, for his explanation. In specific energy levels is only when the electron in the hydrogen atom exists, principal quantum levels. When an atom is said to be ground state is when the electron occupies the lowest energy level, and an atom can only have one ground state. If an electron occupies a higher energy level, it is said to be an excited state. An atom consists of many excited states. With this knowledge is what made the Bohr theory successful when explaining the spectrum of the hydrogen atom. Niels Bohr calculated wavelengths and matched perfectly with the experimental wavelengths, proving the theory correct. Matching theory with the experimental data is successful in science, proving that spectral lines emit certain frequencies, wavelengths. Anyone who is not shocked by quantum theory has not understood it.
There are three types of spectrums: absorption, emission, and continuous. For this work, Bohr earned a Nobel Prize in 1922, and more mathematically complex models based on the work of these scientists that depicted the particle and wave nature of electrons proved more useful to describe the atom with more than one electron. Some important vocabulary you should know when understanding the emission spectrum and Bohr model.